All right, so let's do an elliptical spring with those values right here. So I've got major diameter 20, minor diameter of 10, and a length of 15. Pull that over to the side here. So I wanted to go into the GST workbench. Point out a couple of things to you here. One is the way we would be creating this. If you go to the wireframe toolbar, if you go down below inside the spline here, so go down to helix, spiral, all the way to the bottom, you get curve from equation. So that is the tool we will be using to create our parametric curves, is a curve from equations. So let's begin. So I'm going to first create them as laws. So I'll show you how to create them as a law first, and they will show up on the tree as laws. So to do it as a law, find your Knowledge Advisor toolbar, and it's behind the design table. You will see the fog function. And I've showed this to you before, if I'm not mistaken. So I'm going to call this first law, I'm going to call it XT. And I'm going to need two parameters. The first one will be of type length, and the second one will be of type real. The type of length is going to be the output, and the type of t is going to be the t parameter. I'm sorry, the type of type real would be the t parameter. So I'm going to do a new parameter of type length. I'm going to call this xt. Then I'm going to do another parameter of type real. So notice sometimes you got to scroll up. The real is at the very top. And I'm going to do new parameter of type real. I'm going to call this t. Okay, so I've got an output here, a length, and a real, my two formal parameters. So I want to make this xt, so I'll just double tap xt, or you can just type in xt if you want to. It's going to be equal to, and I've got a major diameter of 20, so I'm going to go 10. I want to try centimeters to see if it works. And then I'm going to, if it doesn't work, I'll go back to my old method of just times 1 centimeter. So I'll go 10 centimeters times, because I don't work in centimeters a lot, but so we'll see how it works. So I've got 10 centimeters, which is going to be the radius, because I'm looking for a diameter of 20, times the sine. So inside of here, as you know, I'm looking for an angular value. And the sine function is going to put out a real number. So let's plug in my angular value. I need 10 revolutions, so that's going to be 20 times pi times 1 rad. And in my notes and what I just showed you, I typed in 20 times 1 rad times pi. Doesn't matter which order you put them in. And then I can go times t. And the t is you've got to have t in your function somewhere. And so here t is a real number, and it's going to vary from 0. It's going to vary from 0 to 1. T always varies in CATIA from 0 to 1. So that's going to make this varying from 0 radians up to 20 pi radians from one extent to the other. Sines and then times 10 centimeters. I'm going to hit apply. If you have an issue with units, and when you hit apply, it's going to tell you you've got an issue with units. Something is not homogeneous. And usually what happens is it's not finding degrees here or radians. It's not finding length here. And the output should be the same as what's here. So this is a length. This total output should be a length. Sine number spits out a real number. Multiply that by a length value should give you a length value. There's a lot that can go wrong here. And I, even as many years as I've been working with this, I still get warning messages. And I go, where did I goof it up? So you just have to dig through. But just remember, it's looking for angular here, and it's spitting out a real number here. This is spitting out a real number. And so I'm going to multiply it by a very intentional length value. If I didn't multiply it by, let's just take this 1 centimeters out. Now, this is a real number on this side, and I'm making it equal to a length. So if I hit apply, I get that warning message because my units aren't matching up. So this allows me, by doing this, I'm saying, hey, that's 10 centimeters. If I didn't put that in there, Katia is going to think that's Katia is going to expect that to be a real number. Sorry, I got a military alert there. Sorry, let me drive on here. So does that, hopefully that makes sense. Now let's do, and if you look over here on my tree under my relations, if you got this turned on, there's my, that's my law for this. Now let's go back and do the law for the X value. That is a design table. So law 2, we'll call this YT. Same basic thing. So I got a real number and I've got a length. Make that real number my T. So real number is going to be my T. The length value will be my YT. So sometimes for these complicated equations, I copy and paste them over from the X side. This one's fairly easy, so I don't have to do that. But here it's going to be equal to, we got a minor diameter of 10, so this would be 5 centimeters, times the cosine. It'd be 10 revolutions, so it'd be 20 times pi times 1 rad times t. Plot, what did I goof up? Oh, there we go. Same principle as before. Now let's do the last one. You've got to have z in this one. Even if your z is 0, you still have to have it. So we'll go zt. So new parameter of type length, this would be zt. New parameter of type real would be my t. So I've got an output here. What T is expecting a length, and this reason it's expecting a length here is because zt is a length value. So zt is a length. So everything on the right-hand side of this equation has got to be equal out to a length. So we know that t is a real number, and we want it to move 1.5 centimeters for every t value. Hit apply. Okay. So there's my 3 values. Let me show you this again. I feel like I jumped over that too quick. So t value. So for every t, 0 to 1, it's going to move 1.5 centimeters. So 1 full revolution will move 1.5 centimeters. Remember, we've got 20 revolutions. We got 10 revolutions. So it's going to move a total of 15 centimeters. So let's go back to the curve from equations, remembering my x and y values. So you can look at my compass. I'm not my compass, but my axis system. So I can come up here and do my functions. So here's my curve from equations. So for my x value, I can select there. My y value, I can select there. And my z value, I can select there. And there is my helical spring. 20 diameter across the major, 10 across the minor, and it's moving 15. That doesn't seem right. Let me find my mistake here. I want to measure this distance. So I went down here to my measure tool. Where is my distance? That looks more like 1.5 to me is the issue I'm having here. I know where my mistake is, but let me. Oh, it's not giving me my link. That's really weird. Okay, here's my mistake. That's 1.5 centimeters from here to here. I made a mistake. I wanted that to be 15 centimeters. So my mistake here, if I go back to ZT, when I was typing this in, I was thinking that can't be right. This needs to be 15, not 1.5. It's the total amount that you're putting it in. There we go. That's more like what I'm looking for. So what you put in under ZT is your total distance. Sorry about that little mistake there. So let me ask you this question. That's 10 revolutions. What if I wanted 10 and a half revolutions? In other words, right now it's going 10, it's going up and going to 10. But what if I wanted it to go one more half revolution around? What would it be?
Would it be 21 in the
It'd be, right. So I wanted 10 and a half, so you got to double it, right? Yeah. So let's see what happens. So come back to here. Let's go 21. What? Isn't that cool? You can get some really cool looking stuff when you're in the middle of changing something. Now let me go to this one. All that was affected because the revolutions weren't equal to each other. Now it should work itself out. There we go. So notice now that's 10 and a half revolutions. Now here's the tricky one. Notice how it's, if I'm looking at it from the top, it's going clockwise, rotating clockwise. Hope everybody agrees with that. What if I wanted it to rotate counterclockwise? Let's go back here. Remember, it's just let's try adding a negative here. This is going to give me really simple. Ooh, yeah. Oof. I wasn't expecting it to require me to do both. That was interesting. Negative and negative, let's see what happens. That should actually, that's still counterclockwise. See the effect? So that's counterclockwise, starting from the top down. Notice how the front and down. So notice how whenever I manipulate the positive and negative, so they're both negative now. So they're both negative. So it's starting at the top, it looks like, and going down. And if I make the y positive, let's make the x positive and the y negative. Verify that that's negative. Yes. Now it's back clockwise. And then if I make that, I'm just seeing the effect of the rotations, whether I enter a and there's a reason why I'm doing this. I'm just not being arbitrary. I mean, I am being somewhat arbitrary, but just notice how adding negatives, notice how it flipped it. Now it's starting on the back side, ending on the front side. So you can affect that by adding the negatives and positives out in front. You can graph that out too, and you think about how that's working. So if you let's look at this from the top. Think about that mathematically. So here's my x direction going down. So my y direction is going out. So if I plot this out, so that's a positive, that's a positive. So it's going to start here because the sign of zero is zero. The sign of 0 degrees or 0 rads is 0. Hopefully you remember that from math. Maybe I should break my calculator out to verify that. So that's why it begins. And then this, so I want to break out my calculator. I don't think I have. Let me see what I have online here. Where's my trig functions? Okay, so let's go cosine of it. Degrees, let's work in degrees. All right, so I'm going to enter a 0 here. Let me go cosine. Let me go sine. So sine of 0 is 0. And then the cosine of 0 is 1. So when you look at your equations, I start off with t is equal to 0. So the cosine is going to have a positive value first because the cosine of y is going to be 1. Oh, I'll let you do the trig in your head, but there's a reason why it starts here and not here in the x direction. Versus, so notice that. Now, if I did a negative on just the y, let's see what happens here. Oops, put it in the wrong place. Then flipped it to the other side on the y. Okay. Now, so just so you can manipulate these starting and ending points is the main thing I'm trying to show you here. Now, what about z? So z is going straight in the positive z direction, 15 centimeters. If I wanted to go down, I could just put a negative in, and it's going to go down the other direction. Now, this is a wireframe. This is a wireframe geometry. You can do whatever you want to with this wireframe geometry that you feel like you need to. I can come in here with do a position sketch, create a reference plane right here at this point, and then do a position sketch with a projection point right there, drawing a real little circle. As we were saying, the spring, right? So I can use the sweep tool, or the rib tool for that matter. That's a better choice for you in the part design workbench. Let's say I did sweep. So I've got a profile. Oops, sorry, the wrong way. Got a profile. Then I got a guide curve, preview. There's my geometry. You can do that with the rib tool as well. So that's a wireframe geometry using just like a helix. So you can do something like this. I could go back up here to connect curve. Where's connect curve? There's connect curve. And I can select that point for my first point, that point for my second point. I can control this with curvature and increase my tensions. Now to where they need to be. I've lost my tree over here. Darn it. Can't play around with my tree. I feel lost. Long tree. Okay, so I can do a join here on these two. Got those two joined together. Go back to the part design workbench. Say I did the rib tool. And so I could do my profile and use this as my join. And interesting looking shape, right? When you agree. Got some is that interference? Yeah, a little bit of interference here. That just means I can increase right here as well. Probably I can go back and increase if I can get to my tree, which I apparently can here. Oh, there it is. I can move my tree over. So I can get back to this connect curve. Just increase that tension value some more. Now I've got some space there. Probably wouldn't hurt. I wonder, I want to try something, and this may not work, but I'll try it anyway. To do a pulling direction. Yeah, that's not going to work. Let's go X, Z. Yeah, see what that looks like. And it kind of flattens out in here. Yeah, I don't like that. Go back to keep angle. Not liking how that curve is looking. See how it's kind of doing some weird stuff here? That would require playing around with that a little bit. That rib is. There's my join. Okay, question so far? I know I'm killing you here, a lecture, an hour and a half lecture. Let me, all right, let me show you a couple more things here. I'm going to hide this. I want to create a parabola. So I'm going to go back to I'm going to stop my recording.